Hi there, so welcome again to the next lesson of Applied Computer Science. Until now we've heard about numeral systems and operations in these numeral systems. We created circuits which represent and, or, and not, and we also built our own circuits so that we could do an addition, for example, of 8 bits, and we created a simple memory with a flip-flop. So this is quite nice, but what is the difference between such a calculator, a microcontroller, and a higher level computer? Now we're coming to the programming aspect. So programming and a mechanism to learn a computer device, an electronic circuit, new things. This is what we want to do today. Welcome to lesson number 4 about computer architecture. Before we start, let's do a short review and have a look what we have learned already. We started with a numeral system. Which was a representation of numbers. In our case, it was a representation with zeros and ones, so that we had the binary system. From this, we created a mechanism of electronic circuits to represent special operations. For example, the AND, the OR, and the NOT. And we thought about this algebra behind, the Boolean algebra. So, having this, we continued to create our own combination. So, we started with truth tables and looked for our own outputs so that we had inputs and output combinations, and then we searched to implement new solutions. So we used Carnot-Weiss diagrams to simplify these combinations, and then we came to things like adders or flip-flops or other things. So from simple new gate combinations to more or less complex combinations of electronic circuits. And with this, we were able to do some calculations. So therefore, we had the possibility to do some calculations. So we were able to combine inputs and outputs so that we got new operations. And with these calculations, we are now able to go into the direction of what is a computer. Here I want to show you a few small things. For example, starting from gates, coming to computers. What is the principle of the John-von-Neumann architecture? How do we write programs for these new calculation and programming tools? What are operating systems? And why do we need higher level programming languages? So, what is the way from a normal calculation machine or based on gates to a computer? Do you remember what we saw in the first lesson? What is a computer? A computer is a general purpose device that can be programmed. So programming is the most important thing. We want to do arithmetic logic operations. Well, we have done this. So all of our gates, the addition machine, the memory, all of this stuff can be used for these things. And we want to process data. So we already know how we can represent data. So therefore we are in a good way. But what is still missing is this part here. What is a programming device? So we have seen that there are a lot of different gates which we can create. We start with a truth table. We define how many inputs we have. And then we can create all of these things. So a lot of gates. So the NOT gate, the AND gate, and the OR gate, which is the standard. Then we can create NAND, NOR, XOR, and all the other parts. With these things, we can create higher level equipment like multiplexers, demultiplexers, decoders, all of this stuff, so that we can identify different inputs and that we can select these different inputs. And with this stuff from here, we can also create these adders. So we can create an adder, a subtractor, a multiplier, a divider, a negator, a shifter, which shifts just the bits into one direction across the byte, for example, things like that. And we can produce memory. Memory is quite important because we have to remember what was before. So we have to remember which number was created before so that we can use it again. So all of this stuff is available now. And therefore, we have to combine all of these things together so that we create something which is a calculation machine, a data processing machine, and which we can program. So what is the programming aspect? Programming aspect means that we create a list of commands which will be processed step by step so that, for example, a new product is created. So how is this programming done? So for this programming, we have to define operations which are processed step by step, so commands. So we need something like commands. And these commands are easily done with this arithmetic logic unit. So I found one in the internet which we can directly use in our Logisim simulator. And therefore, we can directly jump to this Logisim simulator. So what do we have here? So we have input data representing the numbers or other things like character codes. We have output data, so results. And we have a more or less complex structure of a circuit. And the most important thing is now that we can control the behavior of this circuit with some bits which we can set. This is called a control word, and if we set it in a special order, then we define how this internal circuit will react. So in this case, for example, if we want to add, we define here special control words. And for example, an addition means that we have a 1, 1, 1, zeros, and at the last final bit we have a 1 again. So we set 1, 1, 1, and at the final bit a 1 again. And then we can set the input. So for example, 1 plus 3. And then we wait for the clock. Do you remember? A flip-flop with a master-slave structure needs a clock. So we are based on these pulses. So only operations will be done if a pulse, a positive pulse will arise. So if you do this, we do the addition. So the result will be 4. So 1 plus 3 is 4. So for example, if we want to do a decrement,
So we will decrement the A input. So we reset the B input. And then if we decrement by 1, we have to set the control bit. And if you look onto this control bit, it's already the command. So we created now a command which defines that I want to decrement the input of data A. So the decrement is 11000001, and if we set the clock, so we should find 2. If we want to do an increment of A, so let's do a little bit more complex. So it's 7. So the increment A plus 1 would be 8. So we set the increment control word, which is this one. And if we set the clock, we find the 8 in the output. So what we did is we already wrote something like a program. So we started with the addition. We made an addition of B plus A. Then we did an decrement, and then we did an increment. So we sent in 3 different commands, and our algorithmic logic unit processed them. So what we did is we already wrote something like a program. So we started with the addition of A plus B, then we did a decrement, and then we did an increment. And our arithmetic logic unit did what we said. So it processed 3 different commands which came in as a sequence defined by me. So I wrote a program with 3 commands, and our arithmetic logic unit processed them. The thing what I did manually was that I loaded the different commands. So I set the bit sequence here in this control word, and each time a new command should be processed, I set a new bit order. So therefore this loading, and then maybe the setting of the memory, meaning the setting of the input and output data, and remembering the result, this was not yet done by this arithmetic logic unit. So it was done by me, and therefore we need a little bit more. But let's come back to our arithmetic logic unit diagram. So what we did is we made 3 steps. We set the data, we set the operation, we set a clock pulse, and then we got the final result of the data. So these steps must be processed by a modern programming utility. And therefore, this is what a programming device must do. So if we come to a way which can do all of this stuff, we will find the John-von-Neumann architecture. It's not the only one, so there are other definitions, but it's the only one which is still available in each modern computer. You will find a very similar one from Charles Babbage long time ago, but the modern way is this John-von-Neumann architecture, and all modern computers still have this architecture. So what is the specific thing here? So we have an input and we have an output. So we take the input and we convert it to the output using a special device, remembering the arithmetic logic unit. So we process the data. So therefore we will need this arithmetic logic unit somewhere here in this processing utility. But I did it manually, so I set the new commands and I defined the input, and then I started processing here. So what I did manually, we need also. So we need something like a control unit. So taking the data, taking the commands, decode the commands, set everything here, and then say, okay, now process. So we need these 2 things, control unit and arithmetic logic unit. But we also have to remember what we did. So we have to store the input somewhere and we have to store the output somewhere so that we can use it later on again and that we can write it, for example, to the output. So therefore we need also memory. So we need somewhere a possibility to remember what we have done before. So if we go to this, we can think about these 4 different blocks. So I want to combine the input and the output so that you have input and output. It is the use of the commit data and programs. So remember now, we not only send in data. So this is a big difference to a calculator. In a calculator, you have a predefined program. The predefined program is a hard-coded or a hardware which calculates, which does the calculation and nothing more. So you enter data and then you push the plus or the multiplication button and then you get the result. So you do not enter the behavior. So it's predefined. So here we have now, we enter data and programs. These data and programs are stored in the memory or sent directly to the control unit. And then we return the results to the user. So this is input and output. So it's one block. So the connection to the external world. Then we have a main memory where we store also again data and programs. Think in opcodes, in processing codes, in these control words. So if you have control words, you store the control word, which is the command, and the data in the main memory. And then you offer them to the central processing unit. Because if we go back one step, you can combine the arithmetic logic unit and the control unit to one processing unit. And this is the central processing unit or CPU. And then we need in this CPU something which gives us the control over the things which were processed or which should be processed. So we store the current instructions somewhere in our own small memory, which is called the register. And then we count so that we know at which step of our sequential program we are at the moment. So at which line we are at the moment, which command is currently processed so that we can fetch the next one. So we count them and then we decode the operation code or we decode this control word. The decoding can be quite simple, like we did here in our arithmetic logic unit. So we just set the bit sequence in our control word and then the arithmetic logic unit directly knew what should be done. But it can be much more complex. It can be a microprogram so that a special control word starts a sequence of new control words. And therefore, this control unit can be really complex. But nevertheless, it controls the input and output and memory in combination with the arithmetic logic unit. And this is the main control. So the main control of this calculation and logic operations. With this arithmetic logic unit, or short ALU, all of the mathematical and logical operations are processed. So with this knowledge, let's have a closer look into the different parts of our John-von-Neumann architecture. So let's start with the input and output. For the input and output, everything is used which helps us to get in contact to our device, the computer. So nowadays we are used to take touch screens to type in our messages into our mobile phone. You would miss it if you wouldn't have this. So therefore it's a very high level input device. It's also an output device. So you see on the touch screen also the things which the computer produced. So for example, messages coming back. But remember the ALU. In the ALU, we set everything on a very low level way. So we just used input pins to define the numbers and also the control word. And if you can do it with these pins, you can also use things like these holes in a tape or in a punch card. Also, buttons, joysticks, keyboards, other hardware can be used to send data, but remember also programs. So for example, here in this case, we also send in our command. So this can be used for the input. And on the other hand, you have the same stuff on the output. So you can use, of course, as said, the screen of the touch screen. You can use punch cards or punch tapes so that the result is written again on such a thing, or you can just highlight or set an LED, things like that. You can combine several LEDs so that you have a 7-segment display or a hex display. You can have a LED matrix, all of the things. And if you have a LED matrix, you can also create something like a modern monitor or a TTY, so that you have different hardware to get in contact and to take things back from the computer. What is the next step? If we have the input and output, we have to send it to our memory. So therefore, the memory is what you already know, a part in your computer where you can store information. The low-level storing mechanism is a flip-flop. So you set 1 bit, and if you want to store 8 bits, you need 8 of these flip-flops, and then you can set and remember what you have done. So the lowest level part is this flip-flop part, and then you can combine it to matrices or things like that, so that you have a random access memory, which can be reset. You can have also a read-only memory, or you can have something which is similar to a read-only memory, but which can be erased electrically, so that you define a special bit and then you erase it. But it's everything what is currently just available, and it stores, so it's not persistent in the most cases. So if you switch off your computer or your device, everything is forgotten. Only these read-only parts, which are fixed in your hardware, so that, for example, a first startup sequence of your program can be loaded. So in all the days, this was a magnetic core memory, so it really looked like this. So it was really such a network or matrix of this magnetic part here, and it was used to send in, remember, data and programs. We already remember what we also use, the arithmetic logic unit, ALU. So I don't use this, though modern ALUs are much more complex than this simple thing here, but it directly shows what an ALU does. And then we need a control unit. So control unit takes our program or our single command, which is based on an operation code, so the real command and the data. So we send in operation and data, and then we have it somewhere locally in a instruction register, so that we can process on this small piece of zeros and ones. And then we separate the opcode and the address or number. So what we now have is we can directly go to locations in the memory, so that we can say, okay, the next number is on location index 1, index 2, so which is a part of this matrix in our memory, or we can directly send in a number. And then what we do is we do exactly these things what we did in our ALU. So we decode the operation code. Decoding the operation code can be quite simple, as I said. So it's just sending the operation code or the command or this command word into a special input bit sequence, and then say to the ALU, now process with the clock. Or it can also be a startup of a small micro program, so that different other small commands are sent directly to the processor. And then we also count our instructions so that we know where we are in our program, and we do a special calculation, which is again a calculation like with a normal calculations with addition and things like that, so that we can find special numbers in our memory, or that we can find the next command word in our memory. So if you have a look, taking this John-von-Neumann architecture and going to a modern microcontroller, you will find the same stuff again. So I can use this Atmel Atmega microcontroller diagram, and you will find the same things again here. So we will have input and output. So it's somewhere here. So input and output are the bus systems. So single bits or buses and so on. So it's everything where you can get in contact to your device. On a low-level microcontroller, most things are based on single electrical lines. So therefore, everything is based on this bus system. Then we have this memory. This memory, which is not persistent, which is just available as long as the power is on. So is here. So we have a EEPROM and you have flash or something like that. So you have different memories. So remember, ROM, read-only memory. Electrical, erasable, read-only memory. And then we have something like this. So we have a CPU. This central processing unit is our processor here, our microcontroller. So all of this stuff here is a board or a combination of a board which does the processing. And you can find this stuff here, for example, as one electrical circuit, as one chip, which is soldered on a board, so that you have available the input and output pins. So the bus system, for example, for this microcontroller, which is partly directly connected to these pins, so that you can set input and output here, and that you can process data on your device. And therefore we directly jump into this new world of programming. So now we can program computers. And the program is always the same. So you have an input, you want to create an output, so you take a binary coded instruction, a combination of a command with a data set, you take it and you get it from the input, you bring it to the memory, and then you take it from the memory, process it here, use the control unit to define what should be done, and then process it and send it to the output. So if you do this, you do special steps, and these special steps are defined here. So you always do a fetching part. So you fetch data and program. You decode this program. So you decode this instruction, then you execute the instruction, and then you write the instruction back. So this means what you do are these 4 steps of fetching the binary numerical representation of an instruction from the memory into the control unit, into the special register. Then you split the instruction into its parts, especially the operation code, the numbers, addresses, registers, whatever. And then you prepare the processing so that it can be done in the ALU, or so that you can send out information to an external device, or you can define a special location in the memory. Then you execute the processing, so which means you process the command, or you do the operation, the addition, whatever is defined by the ALU, and you control this processing with a CU, so with a control unit. And if you finish your processing. So like with the ALU, what we did in our Logisim simulation, if you get a result, you have to write it back to the memory. And then you continue this. So you take the next instruction, you process it in the same way with fetching, decoding, executing, write back. And the next instruction, fetching, decoding, executing, write back, and the next, and so on. So let's have a look into one of these codes. This is the code for the AT86. So it's a mashing code, and it's exactly this what you heard in the last slides. So you have an operation code. This operation code, for example, defines an addition of a number with a special memory in your CPU called accumulator. And then you have a special number which is arranged in a special way. Do you remember what you heard in the first lesson? Big endian, little endian, least significant bit, most significant bit. Here you have a special setup of that. So you have to know what and where the different bytes and bits are. And then what you do is you take this number and add it to the existing number in the accumulator. And then you have the result, and this result is sent back to the memory. How can you improve this? So how can you make these things faster? So you always have these 4 steps. And what you can do is you can make something like a pipeline. So you fetch the first operation or the first command, and while you decode the first one, you can fetch the next one. And while you execute the first one, you can decode the next one, and you can fetch the third one. And while you write back, you can execute the second, decode the third, and fetch the fourth, and so on. So that you always have more than one of these 4 steps available. So it's a pipelining mechanism. And this pipelining mechanism is quite powerful because it speeds up your processing. It has just one problem. So for example, if you have a jump in your program so that you decide according to special numbers, to a special situation, so that you have a condition. So if you decide according to this condition that you want to continue on another position in your code, so if you have a go-to or a jump to another position, then this pipelining stops here. It's interrupted, for example, and it starts again with this fetching. So you lose, and therefore an optimization is if you optimize these jumps and if you optimize this pipelining process. So what you do is you use a bit stream as command and as number, and this is called mashing code. But look at this number. This number in the AT86 version is not really intuitive. So it's not really nice for the interpretation of humans or by humans. So therefore, there was the idea to simplify these things. So the idea was that these opcodes and parts of these things are just converted, like with a lookup table, into a readable or word-based representation. And this was called assembly mnemonic. So what you have here is nothing more than you have a binary stream, and this operation code here is converted to a text-based operation code. So the number is coded here, but the first thing is readable or human understandable, and therefore it is nothing more. So this is just the representation for this. It's nothing more than a lookup table. So therefore I told you lookup tables are quite important. Also here you just convert this string into this machine code, and therefore this is quite helpful because if you do this, you have always the same processes, and you take this assembly and convert it to the machine code. And this work, or this process step, is called assembler. So therefore, you take the assembly, use the assembler, and then you get this machine code. So it's a text file, for example, then you have the execution file, and then you can load it into your memory and into your processing device. And then a program looks like this here. So it's nothing more than a sequence of these mnemonics, which are processed step by step, line by line, by your device. So, and this nice program does nothing more than writing hello world onto your screen. So it defines the output, so it uses move commands, for example, to take data into special registers or into special locations, and then it sets special, let's say, output pins or output addresses of pins, so that you send out the information which you defined in your memory. And then you can differentiate between processor types. Nowadays it's not really necessary anymore, because nowadays you have this hybrid scenario, so that it's a mixture of both, but you can now think about pure RISC computers or pure RISC CPUs. For example, this Arduino is one. So what is the special thing here? You have just elementary instructions per clock cycle. So each time you have the clock pulse, you have one elementary instruction. So it's exactly what you see in the ALU. It's a very single layer limited gate circuit, a very easy gate circuit. Easy not in this case that the gate circuit itself is quite simple. It's just that you have one layer, so it's no additional separation layer, which has, for example, other programs which must be called if you do a special instruction. So therefore you have a reduced set of instructions. You have to combine this set of instructions to get the final program. You have a huge set of registers, so that you can have a large set of stored information. This is quite fast, because you have everything in registers. You have short and small instructions, so it's quite fast, but the programs become quite long. So you need a high-level language with an optimization. On the other hand, there was this CISC, so the complex instruction set computer, so a CISC processor, and therefore you had a combination. So you had higher level commands, for example. So a command was split into microprograms, and per clock cycle there were several of these instructions, higher level instructions processed. So you have a large set of instructions, and therefore a reduced set of registers. The processing is slower, and therefore the programs got shorter, because each command is split into internal small programs which are then processed. So you don't have to say any step which you want to do. You don't have to tell the processor each small single piece of instruction. So the high-level languages do not optimize too much, therefore. Nowadays you have more or less a combination, so this way of microprograms is quite nice, because you can extend your basic set of instructions, and therefore you have nowadays this combination of RISC and CISC things, using gate circuits, decoder circuits, and instead of these microprograms, so that you have something like a microprogram, but this is inside coded in your circuits. And therefore you load this assembly, you load it into the main memory, then you do these things like microprogramming. You decode it to a machine code, and this machine code is then fetched, decoded, executed, and write back or wrote back to the memory. So you have several of these processing loops in your processor. But the problem is now that each vendor of a processor can now define its own, let's say, commands. And therefore you have individual CPUs and therefore also individual assembly mnemonics or machine code bit streams. And therefore each CPU must be programmed individually. And therefore it's not so nice that you write the program once and then you load it onto different CPUs. You always have to write specific things for your CPU. And therefore we come to the next step. We come to the operating systems. So what we do now is we set a higher level part onto the lower level programming. So we define a standardized mechanism to talk to your computer so that you don't have to program everything from scratch. You have a predefined view onto your device, and what the operating system does, it gives you the possibility to have clear interfaces, and beyond this or under these interfaces, beyond you have the higher level work, and under this interface you have all of these very hardware specific parts. And therefore we have to go into this set of operating systems, and I take one which is related to the Linux system because I think it is one of the most intuitive operating systems. All of the others are of course similar. They are mixtures of these layers, but in principle they are the same. So what you have is you have the physical device, you have these microprograms, hardware coded or whatever. You have this machine code, you know, this assembly stuff, so which is specific. All of this is very vendor specific. And then you have the operating system part. This operating system part is based on a kernel, which is the internal part. So everything what you need to control this stuff here. And then you have additional things which help to deal with this stuff here. So you have, for example, shells, editors, graphical user interfaces, compilers, batches, all of this stuff already available in your operating system stuff. So, but the real hard part which is connected to this stuff here is this kernel. And then on top of this operating system, you have the rest. All of your user programs, all of your games, all of your applications, apps, and other things what you see directly if you contact your computer. So there's one additional thing on your computer. To be able to run this higher level operating system, the computer must be brought to a general mechanism, and therefore the BIOS is used. So this basic input output system, so that not everything what you need here for the interaction with the external world, for example with external cards or external devices, must be completely programmed here. So this is what the computer brings with itself, so that you have a fundament of basic operations. Then you use the operating system in combination with this stuff here, and then you have these higher level things which you can define. For example, if you're able to program, you can do all of this stuff here. So what is part of this kernel? So let's have a look. Part of this operating system kernel is, first of all, this abstraction which I mentioned, so that you don't see the lower level hardware and its specific things, so that you just have a clear predefined standardized interface. Usually in programming languages, these things are called system calls, because you activate system specific programs or routines. Then this operation kernel is application independent, so that all of the applications above just use this kernel, but it's not related to them. They can share resources. They do this critical section management. For example, if you have just one output interface to monitor, or if you have a keyboard, you have to share this keyboard between different other programs or different other users and things like that. So this resource sharing is quite important. Then memory management, of course, so that the memory which is used at the moment is optimized, so that you have not too many gaps. For example, if you always create small pieces of memory, you always take the next one, and if you release the memory again, so if you free it, then you will have some gaps. So this reorganization of memory, things like that, is also part of this kernel stuff. Then, of course, the management of the programs, usually combined as processes. So if you start a program, then you have a process which runs this program, and this is also managed, so that you have also a multitasking, multi-user environment, so that more than one user can use your computer, and that more than one program can run on your computer at the same time. More and more complex and important part is the security. So security means that the computer cannot be attacked by programs or by external hackers or some critical situations, so that you have special modes there. You organize the disks, the file system, and you organize the lower level hardware control, like the drivers. So if you plug in a USB cable with a special device, then everything is automatically installed and you don't have to think about it. You just have to use it on a higher level abstracted interface. All of the things like networking or organization of print events like spooling or interrupt handling. So for example, if you get a message from the hardware network card, or if you have a special situation on a communication line, then you interrupt the country running programs and do this. By the way, the Microsoft DOS, one of the first operating systems, Microsoft DOS 1.0 in the year 1981, was a single user and single tasking operating system, and it consists of 4,000 lines of this assembly code. So it was really the starting point of such high level programs. So therefore it was a very new thing to have an abstract layer in these years, and it was the very high level breakthrough that you had this, because all of the higher level parts here do not have to think about what is on the lower level things, and the operating system designers prepared it so that it runs on different hardware. This is quite important. Modern operating systems like the Linux kernel are of course written in higher level languages, for example in C. Like Linux kernel is written completely in C. Let's have a look what is meant by this abstraction of hardware layers. So it's very specific that you have for the programming or for the connection by programs on the higher level part, you have a predefined, clearly defined interface. So you have an interface definition which just tells you what is allowed, what you can call, how the system call is organized, so that for example how it is built, how it is named, what you can hand over as arguments, what you get back, things like that. And then the rest, the, let's say, device control, the hardware drivers, all of this stuff is done inside this operating system stuff. So for example, you do not have to know things like where is the address of UARTs, like serial communication or network stack things. You just have to think about send a message, open and send a message, or open a file, read from the file. So you don't think about how it is organized in the lower level parts. Basic input and output methods are organized like that. So as I said, these things like file access, you don't have to read directly some sequences of bits and bytes from your hard drive. You just read one complete block, for example, organized in lines, so that you think in files and lines and things like that. So this is quite comfortable, and therefore the operating system is one essential part. Here's one sample which directly explains this file stuff here. So what you have here is, for example, a representation how it might be on the hard drive. So this means you have the hard drive here, and you have organized blocks, physical blocks of bytes and bits, so where you can set different blocks and write your data. And then it walks through the complete layered model here, and it arrives here on the higher level parts, so that you see on the other hand on the higher level explorer or file system organizer that you have a structure of folders and of files. And therefore this is quite nice. So you don't have to think about the lower level things. What is also done is that you have a mechanism of processes which run one by one. So this was also the first thing what happened in operating systems. So you started a program, the complete program worked completely, run through the whole stuff, and then it finished, and then the next program started. You see it here, for example. You have here the different programs. So the first program starts, does all of the stuff. So it is now unique. So it means it can use all of the resources completely without restrictions, because there is only one program. For example, writing something to the monitor, something like that is completely unrestricted in this case, because there is only one autonomous access, and then the program finishes and it hands over to the next program, and so on, so that each program has the resources completely for its own use. So there is nothing to organize. You just have to organize how the sequence is loaded. This is called batch processing. It was one of the first things which happened. If you stop the complete running, then it removes everything from the stack, and then it's gone, and a new startup goes on. Another method is an organization which splits into pieces. So let's have a look. What is the batch processing if you have different processes? So let's talk about, for example, here 16 processes. The 16 processes have different arrival times. So you see that some processes arrive directly at the beginning, some processes end or arrive later on, and then you have different run times. So some processes last longer, some processes are quite short. So it's something like you arrive at a cashier's desk, and there are different customers, and they want to do things. So some of them need more time, some of them need not so much time. So therefore how do you organize this queue that it is a relatively fair process. In this way, the batch processing just first come, first serve, and then it walks through all of these things. So for example, in this case, it's not even first come, first serve. It's just it walks through all of these processes according to the process number, so to the process ID. So it's not a really fair mechanism. So first come, first serve, for example, would be that first of all this is, then this, and then this, and then this, and so on, so that you have a little bit of fairness. So it's like with this cashier desk or whatever. But another mechanism deals with this so that it is more fair, in this case that you have small slices of processing. This means you split your program into pieces. So you have the different programs again, so in this case, for example, 3 programs, but you cut it into small pieces. So you separate your program, which means that you can start with the first part of program 1, and then you interrupt it. So the operating system interrupts the program, remembers, of course, everything what is in the memory. So the location of the command counter, all of the things which are stored at the moment in the memory or in accumulators, in registers. So everything must be brought into a persistent memory part, and then the next program is started. So it loads everything from the previous situation of this program into the current registers and things like that. Then it continues a small step, and then the same stuff again. So everything is shifted to the memory, and the new one is loaded. But the big advantage is that program 1, 2, and 3, for example, in this case, are operated almost at the same time. So if you cut these pieces into such small time slices that the user does not mention it anymore, that there are interrupts, then it looks like you have a parallel processing, even if you have just one resource of a processor. So therefore, this is what is usually done. Like now, for example, if I do the recording, if I watch the PowerPoint presentation, then you have these programs completely at the same time on your computer, but not all programs run at the same time, so they share the resource of a CPU in the way that you have this time slicing. What you have here is a so-called scheduler. The scheduler can be shown like this wheel, so that, for example, you have a pointer, now this program, now this program, now this program, and the scheduler and the scheduling mechanism is called round robin, so that you always have another process, and if no process is active, then you have a special operating system process, which is called the idle process. The complete mechanism is named preemptive multitasking, because this preemptive means that the operating system interrupts each time, and then it organizes the time slices and all of the programs which are currently active. So if each time you start a program, it becomes a process, and each time a process is active, it is in this time slicing process, and then you have this organization. So what does it mean? Several programs are in the memory at the same time and alternate on the CPU. Then the program calls or system routines or interrupts are required so that you can connect the devices, and then a manager, a scheduler, organizes who is next and how is it organized. So there are, of course, different mechanisms again. So you can have something like a prioritization, so that you take first of all tasks which are high priority, so where, for example, users wait on interaction, and you reduce processes which run in the background. So things like that. So you can have a prioritization mechanism, or you can have a real round robin with fair, completely same valued processes. So there are different mechanisms. So it would like if the cashier behind the desk has more than one window and always changes from window to window, so that they're different mechanisms to almost parallelly work with the customers. Okay, how does it look like now? So all of these yellow parts are the times when the processing is done. So if you watch here, so it starts this 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 and a new process starts. So all of the processes are operated during the time slices. So all processes are active, and at the end only the process which is not yet finished continues. And if no process is active, you have this idle process. So if you look onto this, you always have small pieces, so where the different processes are active. So they are not active at the same time, but it seems, or it looks like it would be like that. Okay, so therefore it's a quite helpful, a quite handy way to have interactions with users, for example, and also processes in the background. A big problem here, or a big issue, is that you now share also resources. So if, for example, if you have access to the network, what happens? So two processes want to send messages to the network. So a network is one cable, so it's one line. So you have to reserve this line. So you want to send out your message. And therefore, if two processes, for example, if the first process is interrupted directly during the sending, then it might happen that the message sending does not work correctly. Or if you want to write something to the monitor, for example, in the case here where we have two processes want to write hello world. So if the first wrote the age and if the second starts also, then you have the output of two programs as a mixture here, which is critical. So therefore you have to think about mechanisms to have atomic operations. So they must be non-interruptible. And therefore special system calls must be protected by the operating system, that they are not re-entrant. So for example, things like sending a message to the network or other things, they must have a special mechanism to be non-interruptible. Okay? And this is one thing which always makes problems. So believe me, it is one thing where we had for our complete programming, especially in graphical user interfaces. For example, the graphical user interface is the thing where the user gets information from your program, but in the background the real operation is done. So it's just the feedback of information to the graphical user interface. So you have two of these processes, and they have to organize each other so that they do not interrupt themselves. And believe me, they're the most problems because, for example, strings or text messages, if you remember, text messages are a combination of ASCII signs. So it's not only one small 4-bit block, it's a sequence. And if you have dynamic memory, so that the size of these messages can be adaptable, so like for strings, then you have the situation that the memory which you require for that is separated from a location of the address. So it's just a pointer to this memory, and this pointer to this memory, for example, is the location, or it points to the location of the text. And if you change this so that you resize these things, then there happen a lot of activities in the memory. For example, the old memory is freed, a new memory is created, the information from the old memory is written to the new memory, things like that. If you interrupt, then addresses between old and new memory are not consistent anymore, and then you get a crash. And this is a very, very essential thing what always happens. So for example, strings, especially strings in C++, have another situation that they save time. For example, they have a so-called reference counting. It means as long as the memory or the content of the memory does not change, as long I keep it, I do not change it. I just put addresses or links to this position, and after then I change it. So if two processes work with the same information, for example, the process in the background doing the work and the process in the foreground showing the information, so if both access the same message to work with it and to show it, to send messages or whatever, then it can happen that this reference counting says, oh, there is no change, and then that both processes change during this time slicing mechanism the same memory, and then you have a program crash. And that this does not happen, you have to work with these restrictions, which are called critical sections. So you have periods of your program which are restricted, so that only one, and really only one process works with the data, for example. So in our case with a string, if you have a string and if you manipulate the string, as long as you change it, no other should access it. So no other should change also addresses or content. And therefore it's similar to what you have with a traffic light. In this case, just with green and red. So if it is green, so you ask, is it green? Then you block it, so you set it to red, and then you do your work. So if it is red, no other can access it. And then you do your work, and after then you switch from green to red again. From red to green again. A problem here is now that you have to ask, is it green? So if two or more processes ask at the same time means in their own time slice, but in following time slices, if they ask at this same time period in their processing, is it green? And if they are interrupted there, all processes will get the information, yes, it's green, and they will again run into this problem. So therefore this asking and setting must be non-interruptible, so it must be atomic. Okay, and therefore it is called, or that there are special mechanisms which are called semaphores or mutexes. So mutual exclusion, mainly used in graphical user interfaces. Semaphores are in the lower level operating system stuff. So remember, it's nothing more than a traffic light, but with a special case where you have the situation, is it green, and set in one non-interruptible block, so that you have this in an atomic scene. Well, in this world it should work quite nice, but now you have a situation that one process can influence the other process. How? So let's have a look So if one process waits on the traffic light becoming green, and the other process never will set it again to green. So if it takes the resource alone without any, let's say, social contact to the other processes, then this process will starve. So this process will never have the chance to do the work. And therefore we have now influences between these different types. And therefore we can define two special scenarios. So one is the starvation and another is the deadlock. So what is the starvation? It can happen that some processes are always blocked when requesting a hardware resource. So it's what I explained. Or it can also happen that you have a cross-link between two processes, so that two processes block each other while waiting on a hardware resource. So that one process waits on the other process and the other process waits on the one process. So that you have this cross-link between these two processes. So these two problems are quite similar, and they are one of the things which make the most problems, as I said, in dealing with graphical user interfaces. Before we continue, let's have a look to the same stuff again, just with some samples. Imagine you're at the supermarket and you want to pay, or you're at the postal office, so you have the cash desk. So you have one cash desk where the cashier sits and awaits the customers. So, and they queue up and wait. So this is the batch mode. So you have the first come, first serve. So the first one arriving will be served. So this is the so-called batch mode with first come, first serve. The difference to this multitasking, preemptive multitasking, is now that it looks like the cashier has more than one windows or caches. And is always at one position where one of the customer is waiting. So, and what does he do? He jumps now between the customers and always does a little piece of work. Okay? So, what is now this interrupt? This interrupt, for example, is that a new equipment arrives, for example, or that the package must be brought to the truck. So there is an interaction where one single resource is. So that you have directly the resource at this moment, and now you have to deal with this, that you organize this between your customers. So this is this multitasking part. And imagine that now, for example, the first customer never returns the cashier. So, for example, the first customer talks and talks and talks and talks, and there's a direct block of this person behind the window. So there is no chance anymore to jump to the next one, and therefore all of the others wait. This is this starvation situation. Okay. Another situation can be that, for example, there is no problem to jump between these two windows, but the customer 1 waits for customer 2, and the customer 2 waits for something from customer 1, so that both wait on each other, so that you have the situation, you have a block again, so nothing will be done again. The rest, for example, works quite well. So our person behind the window, so the service person can jump between the different access points, but there here two customers which will never end and which will never have the chance to proceed. And this is the deadlock situation. Okay? What you also can do is that, for example, you prioritize this mechanism. In this case, all of the customers have the same priority. So it's the most social thing. But of course, there are people who have just, for example, one letter instead of a package. So a letter is much faster to process than a package. And therefore, it would be quite good if you arrange it that you have, for example, the shortest time first, or that you have prior persons, so that you have the same situation here. You have a switching service stuff, and you have now the priority. So for example, you have again your customers, and now this has priority 1, this has priority 2, this has priority 3, 5 and 4. So what you do now is you do not use always the next one, you search the next priority. So in this case this, in this case this, 4, 5. So that you organize it in another way. So for example, in this case, shortest time first. And you have, of course, mixtures of these systems. So what you should not mix now is that all of this works on one CPU. So this is multitasking, or a multiprocess system and not a multiprocessor system. So in a multiprocessor system, all of these mechanisms are parallel on separated processors or on separate CPUs. So multiprocessor or multi-core, the situation is like this, that you not only have one of these service guys here, you have more of this. So for example, let's say we have 4 cores. So we have core 1, core 2, core 3, core 4. And on all of these cores, you have a real parallel run. So there can be interaction between these cores. So there can be interaction between these customers, which again lead to things like this here. But in principle, all of the different cores deal with their own customers. Okay? And therefore you have a different scenario. So for example, if you arrange in your modern computer system that each program is on a different core, then you have a real parallelity. if you have it here, then it's just something like a parallelity. So it just seems like parallel, but you have this time slicing. Let's jump back to our slides. So what you can also have is that, for example, each process, so each complete program, is again split into small pieces, so that, for example, you have different, let's say, small program paths which should run in parallel. So you have to split between a program which starts, it's a process, and inside parallel loops which should work like parallel. These things are called threads. So you have a program which is a process in your operating system, and then you have small parallel loops inside your program, and there you have again something like processes, small processes, which are called threads. So different threads or thread loops in your program. On the Windows, all of the processes are called threads, by the way. And the Linux, you have both. You have these POSIX threads, and you have the process mechanisms. So just for completeness. But the principles are always the same. It doesn't matter if you have threads or processes. You have to always deal with these interconnections between the processes. You have to deal with these critical sections. You have to deal with these mechanisms to have a fair processing, and that no process will starve. On the other hand, you have to organize that the processes can interact with each other. So this is one of the cases where these critical sections can happen. So for example, if some process wants to talk to another and does not send the message, and the other process waits and waits and waits. So there are these interaction mechanisms. But it's a quite important thing that the processes can interchange or exchange data. So, and therefore we have this mechanism that there are different ways, and this part is called the inter-process communication. So inter-process communication means you have the processes in your time slicing mechanisms and your round robin mechanism, and then you have different ways to exchange data. You can use, of course, memory. So one process puts the data which should be sent into a special position in the memory, and then another takes it. So this shared memory is a very efficient way, but it just works on one computer, of course, because it must the processes must share the memory, and therefore it must be on the same hardware. And you have to deal, of course, with these traffic lights, you know, with semaphores. So if you change the memory with both processes, then it might lead into a critical situation. So this is one mechanism. You can use the memory. So things what we already have available. You can also use high-level operating system stuff. For example, you write with your abstracted interface to the file system. You write a file, and the other process reads the file. So it's also nothing more than communication. So this is usually called pipe. So in this case, you use directly the memory, so it's more or less a hardware-based thing. Here it's an operating system-based thing. So you use the abstracted interface of the operating system. And then you have another mechanism. It's again a special stack in the operating system. We have two processes, and you open a communication channel. These two things here are related to one hardware. So if you want to open the file, you have to be on the same hardware. These here can also work between different computers, because if you're connected with a wire, so if you're connected with the Ethernet or whatever cable, then you can use this mechanism. So it is a special interface with a special protocol So with a special mechanism to say, hello, I want to send you data. Oh, well, please give me the data. Here are the data. Thank you for the data. Thank you for the processing. Bye-bye. Okay, so you have a special mechanism between both, and you have a special electrical definition, so that you have a special hardware interface again, which does the interprocess communication with sockets or with higher level communication mechanisms. So you do a send and a receive. So these different interprocess communications are always used here. And then another thing is where we have to separate from this multitasking is these multi-user modes. Multi-user modes mean that you have access to your hardware by different users. On your laptop, it doesn't matter. So just keep in mind that you should always have an administrator user and a normal user, just for security issues. So do not do your regular things with an administrator. Do the normal things with a special user which cannot change the operating system. Okay? The normal user who cannot change the operating system. This is quite important. And therefore you have already, if you do this on your computer, 2 users. Maybe at this moment they are not logged in at the same time. But if you think in Windows, you can open the administrator and another user. On a server where you have a centralized IT, so you have more than one user available. So if you have a database system, or if you think in search engines, you have millions of users at the same time, so they're sending the requests. And therefore, you have to organize the user setup. And different users should have different rights. Remember, administrator, normal user. So administrators can change parts on your operating system. Normal users should not do that. And therefore, for example, if you download a web page which is an attacker to your system, in a normal user it's much more safe because it cannot change things in your operating system, cannot install things on your computer. Administrators can do that. So you have different user rights, and therefore you have to organize these things. So for example, you have to do things like account management. So you have a name, a username, and a password. Or you have a username and a key file. Or you have a password, key file, passphrase, and whatever, password. So you have different scenarios, and according to these credentials, you organize which rights the user has. Another thing is, if you organize this, then different users should not have access to the files. So therefore the file system must be organized so that, for example, users can only write or read or execute special programs. So this is nice in Linux. For example, if you watch here, this part here, you see files which has the RWX tags. You usually have a tag for your own access. You have a tag for your group, so you can group users to new user groups. And you have the rest of the world. So usually you have 3 of these blocks, and you can set, are they allowed to read my file? Are they allowed to write into my file? Or are they allowed to execute a program? So all of these 3 blocks have this RWX, for example, in Linux, and therefore you can define what others can see. Also, folders have the same stuff. What others can see and what others can do on your system. A lot of things, you know, but you see how efficient an operating system must be and what is content. So and this is just the basics. So there are several more things what are part of this operating system, so that you just switch on your computer and everything works quite well. Okay. there was one problem now. Do you remember we wanted to abstract the hardware? So if you go back to our first lessons, so we were able to produce something like a circuit with ands, ors, and nots. We combined it to a calculation utility, to a programmable calculation utility, and each vendor had his own operation codes, their own mnemonics. And then we thought about, oh, let's create an operating system. So the operating system hides all of this uninteresting stuff. Okay? But remember, I talked about Linux, I talked about Windows, there is also Mac OS, there are several others. Also real-time operating systems, for example, Foxworks, and so on. What do we have now? We have the same situation again. The different interfaces from, for example, from the different operating systems are again different. So if you want to write higher level programs, you have to focus on the different operating systems. This means if you write a program for Linux, then it will not run directly on Windows, or it will not run on Mac OS, and so on. So therefore you have to write your own programs. And in days of modern mobility with different smartphones and things like that, you have Android, you have other operating systems on these devices. It's not so nice if you write your app and you have to write it several times, and the app does exactly the same. Okay, so therefore we have to find another abstraction layer, and this abstraction layer is usually called a middleware, a distribution platform. And what you have with Java or modern higher level programming languages, you have such an abstraction layer so that you don't have to think anymore about your lower level things. So in the starting point it was Corba or other such level abstractions, so that you have the same situation like with the operating system here for the hardware, you have the same here for the operating system, so that you have one standardized common interface for your user programs, for your applications. For example, it is quite essential for distributed clocks, timing, all of the things, service organization. So for example, you just send out a call and say, okay, I want to do this, can you help me, and things like that. And then the direct app which does the processing can start on your machine. So things like that can be organized with such a middleware, and it's just again a new abstraction layer. Okay, so now we have everything. What we can do now is we can create our own stuff. So for example, we can build such a nice hardware. So this is a robot. Here is the microcontroller. You see? Here are some external interfaces. So you have a mechanism to talk to this. So it detects things in its environment. So you can even navigate. You can control hardware. For example, you can control the different wheels. So you have everything what you need. It's great. But writing assembly code or writing machine code in principle, because assembly is just a mnemonic of machine code, and also maintain this stuff is quite difficult, and therefore it's quite essential that we deal with higher level languages. So programming such a robot, which might be the future of a vacuum cleaning robot, or things like that, using assembly would be a mess. Okay, and therefore we have to think about higher level languages. What are the advantages and the disadvantages of our current situation of programming? So we have assembly, which are the mnemonics. So assembly is a easy representation of machine code. Together with the operating system, with this interrupt, with the hardware components, we can use it. So we have to adapt it to the specific machine code. The code is quite compact, so it's just what really runs on your hardware. But there are big disadvantages. The programs become large. So, and they are often confusing and difficult because, for example, you have a lot of jumps. If you want to repeat things, you have to jump back to a previous line counter or command counter, things like that. So it's difficult to understand what happens there. The architecture is very different. It's very bad maintainable and portable because it's very specific to the hardware, and therefore it's error prone and cost intensive. So the way to write assembly on hardware is just in the lower level part. So if you want to do, for example, a fast memory copy or something like that on your mobile phone or whatever, then you can do these things. But for all of the other things, programming of higher level graphical user interfaces, this is not the ideal way. And therefore, we have to think about how can we arrange our process work, how can we describe this stuff so that at the end we have a very comfortable way to tell the computer what it should do. And so that we can, for example, have very small tiny pieces of equipment like this here. So it's again a small microcontroller, and we have here an infrared LED. And for example, this is a replacement for the automation of a remote control of a TV. So we can program these things with assembly, but it's much easier if you write, for example, C or C++ code, because then we can replace these things. So we need a mechanism to simplify our life in creating programs. That's it. Next week we will talk about languages. Stay safe, and we'll see each other. Bye bye.